Okay. Got it. So, okay. Well, thanks again to the organizers for inviting me to give this talk here about our recent work together with Daniel, everybody knows of you, and David, a student here in Madrid. Paper is published now in JHAP and has this archive number. Okay. And yeah, the title of my talk is Pseudospectra of Holographic Quasinormal Modes. So there's a lot of pseudo and quasi and things like that. You will see what that means. Okay, so here's the outline of my talk. First, I will talk a little bit about quasinormal modes. Now, this is probably in front of this audience a bit redundant because all of you know quasinormal modes and you know their importance, but just to remind us a little bit also about the role quasinormal modes play in the gauge gravity duality. And then I'm going to define the concept of pseudospectra. This is a surprisingly little known method or theory which has been developed by applied mathematicians. And I think they're very, there's some very important message for us there. And we will apply this method or idea of pseudospectra to quasinormal modes in asymptotically anti-de Sitter spaces and try to draw some conclusions. There will not be too many conclusions because it turns out that the problem is extremely complicated and has many mathematical aspects, which I usually, you know, as a physicist, you don't care about it so much, but here apparently it comes back and haunts you, and one needs to understand much better some of these properties. But in order to start, I just want to review something which, you know, everybody knows and which is sort of the greatest, best example of say what appears in the physics of an oscillating string or in quantum mechanics or whatever, and that's the eigenmodes, say, of a string. So you take the wave equation and you look for the eigenvalues lambda of that equations with certain boundary conditions. So here in the simplest case, we have Dirichlet boundary conditions such that the amplitude phi vanishes at the endpoints, which conveniently here I've just chosen to be 0 and pi. And then we have this differential operator, and if we define a sort of inner product between state functions phi and psi, then with this inner product, we know that and these boundary conditions, the operator is self-adjoint, and we can show this just by doing partial integrations. And so this equation holds, and this tells us that the eigenvalues have to be all real. And in this very simple case, we can, of course, construct the eigenvalues and eigenfunctions explicitly. So this is all very well known and the cornerstone of you know, quantum physics and lots of physical applications of this. Now, what are quasinormal modes? Well, in quasinormal modes, you know, they appear in the physics of black holes. And famously, you know, black holes don't have hair, so they swallow everything, every excitation, particle or whatever you place into a black hole background, it eventually falls behind the horizon and disappears. At least classically, you don't see it anymore. So if we think of this as being some excitation in a field, then this field excitation has only two possibilities. Either it falls behind the horizon, or if you're in asymptotically flat space, it might also radiate off to infinity. And eventually that means that this perturbation will die away and will vanish from the spacetime. So you can formalize this here. For example, you have this spacetime, which is here supposed to be an asymptotically flat black hole spacetime, say a Schwarzschild spacetime. You expand the field, the scalar field, into spherical harmonics on the two-sphere, make a Fourier transform in time, and then you look for these radial wave functions, which are solutions to this this wave equation, to this equation. Under certain boundary conditions, and the boundary conditions are, as I argued, they should be such that on the horizon, the wave has the form of an infalling wave, or actually outgoing if you take the point of view of the domain, which is outside the horizon, stretches out to infinity, then from the point of view of sitting in this domain, you know, this is an outgoing wave at the horizon, and it's also an outgoing wave at infinity. So you can call this outgoing boundary conditions. Here I've introduced this R star coordinate, which is related to the R coordinate by this equation, where F is the blackening factor of the black hole. So here R star on the horizon is equals minus infinity. And you can do that. So now you have a second order differential equation. So you have two boundary conditions. And this leads to a quantization condition on the frequencies omega. And since these boundary conditions are such that the field eventually has to go to zero, so that means that the frequencies have to be complex. And in these conventions, they have to lie in the lower half plane, such that eventually you get an exponentially decaying field amplitude. And so these quasi-normal modes, they can be calculated. And here's a very old calculation. So this was not the last version. Again, I forgot. This is actually from an old paper by Lieber, I think it's from the 1970s. That's the black hole spectrum of a Schwarzschild black hole in asymptotically flat space for different values of the angular quantum number on the sphere. And his convention is just opposite to what we use usually in ADS-CFT. So for him, it's exponentially damped if the imaginary part is positive. So think just this is minus imaginary part of omega here on this axis. And you see a discrete spectrum of quasi-normal modes. So they typically have a real part, which gives an oscillation, and then this imaginary part, which describes the damping. Now, since from the black hole perspective, what goes into the determination of this spectrum of damped modes are just the characteristic quantum numbers now, characteristics of the black hole, which are its mass and its spin, and possibly its charge. So these determine the quasi-normal mode spectrum uniquely, and this led to the idea that you could do some sort of black hole spectroscopy if you observe, say, the frequencies in the late phase of the ring down, say, of black hole mergers as they are measured now by gravitational wave astronomy instruments such as LIGO. And you could resolve these frequencies, then you could, measuring a couple of frequencies, you could determine in an independent way the properties of the final state of the black hole, its mass and its frequency, and so on. So, well, at the moment, this program seems to be challenging, and typically not much more than possibly the lowest mode can be identified. Also, there are claims in the literature that one can probably identify a second mode, but it seems to be a very, very complicated business to really bring this to success, this program of black hole spectroscopy. And one of the problems is what I will discuss in this talk, namely that this black hole, these frequencies are very susceptible to even small perturbations of the space-time, and they can change a lot. So that's all I have to say about asymptotically flat space-time, and then attempts to use this quasi-normal mode spectrum for practical purposes, determining characteristics of black holes in the final state of black hole mergers. But of course, here we are interested in holography, and well, this is just a standard slide of what holography does for you. Gives a dual of a strongly coupled quantum field theory, is a weakly coupled gravity theory in ADS. So I can be very quick here because you know these things all perfectly. So what are the holographic quasi-normal modes? Well, Here I have written down the metric for the Schwarzschild ADS black hole with a flat horizon. So here the dual field theory really lives in Minkowski space. And I've replaced already the horizon, the event horizon of the black hole by its Hawking temperature, T. And so we can solve wave equations just as before in this black hole background. We can expand on Minkowski space to a Fourier transform on the spatial coordinates and on the time coordinate. And so we get just this exponential function here for the eigenfunctions in time and space. And then we get the wave function. And so the wave function, again, on the horizon, we demand this infalling boundary condition that it's just a pure left-moving wave at the horizon. And then on the boundary, we know that we can expand this a general solution into a leading and a subleading term. When the holographic dictionary, the leading term has the interpretation of being a source for an operator whose expectation value is eventually given by the subleading term. So, and with this holographic dictionary, we can actually define the holographic or dual retarded Green's function, which is basically given by the ratio of this subleading term, also the normalizable term, divided by the non-normalizable, the coefficient of the non-normalizable solution at infinity. And now we can define the quasi-normal modes as the poles of the retarded Green's function. So this is an excitation which is purely the subleading term, and so it can live in this it's a finite energy excitation which can live in this spacetime without being excited at the boundary, whereas say for general frequencies you would have to introduce a source term as well. So these are actually the poles of the holographic Green's function. Okay, and this goes back to this seminal papers, yeah, by these authors. Good. So for a simple example, for example, in BTZ black hole, you can actually solve for this holographic Green's function explicitly, and you can calculate the exact spectrum of quasi-normal modes. And so this is given here. I'm actually not sure who did this first, but it appears in several papers and reviews. So all of you have probably seen this already. So it's indeed a spectrum of isolated discrete points in the complex plane, and they all, in this BTZ black hole, they all lie in the lower half plane. Of course, in a more general background, like in ADS5, Schwarzschild ADS5, then you cannot solve for the holographic Green's function explicitly anymore. In most of the cases, there are some special cases where you can still do it, but generally you cannot, and you have to resort to some numerical procedures to solve for the quasi-normal mode frequencies. And so this is from an old paper by Andrei, where he calculates quasi-normal modes of scalar field. And in the meanwhile, I think this structure of quasi-normal modes has gotten its own name. It's called Christmas tree. I've got it several times. Okay. And of course, most importantly, what we learned over the years of doing holography, one of the important things is that if you look to quasi-normal modes, which are associated to gauge fields in the bulk, then those correspond in the dual field theory to currents, conserved currents. And so there's a conservation law in the dual field theory. And this suggests that there should be a way where at long wavelengths, so Q is an absolutely conserved charge. So if you go to long wavelengths, in the dual field space, then this charge cannot disappear, but it might disappear if there is some wiggle in this charge. These wiggles can disappear, and so naturally this leads to hydrodynamic modes, such as diffusion, for example. And so typically, if you have a gauge field, you have a scalar channel, which is the transverse channel, so there's no diffusion, but there's this longitudinal channel where you find a diffusive mode, and which to lowest order in an expansion in the wave number k indeed fulfills this diffusive law. And then, of course, higher quasi-normal modes and so on, and there's an interplay between these guys, and there are several, this has led to quite a renewed understanding of what hydrodynamics really is. And for example, you can think about hydrodynamics as a derivative expansion, taking this lowest order approximation to this dispersion relation. Again, here I've plotted minus the imaginary part. These are the dots here. These are the highest modes, and I think the blue parts are the imaginary parts, and the red are the real parts of these higher quasi-normal frequencies. So you can expand this to higher and higher wave number. What you see is that it starts out like nicely quadratically, but then somehow it becomes super quadratic and higher. There's a whole story related to that, which has to do with causality and so on, and that and resummations, which has become very prominent. And then, for example, there have been ideas put forward which say that hydrodynamics is an effective field theory, and you can understand the validity of to which wavelength hydrodynamic description might be good by looking to the points in this complexified space of complex frequencies and complex momenta where the analytic continuation of this hydrodynamic mode collides with the first non-hydrodynamic mode. So there are lots of interesting phenomena related to this. And so obviously quasi-normal modes are really an essential ingredient in the gauge gravity duality and in its dual interpretation as, say, encoding hydrodynamics and transport in general. Okay, now what are pseudospectra? So pseudospectra, there's a very thick book by Trefethen, by mathematicians, applied mathematicians Trefethen and Nombre. And the essential ingredient here is that we have to understand quasi-normal modes as eigenvectors and eigenmodes of non-Hermitian operators, right? Since we are dealing with an open domain in which the perturbation eventually dies out at infinity and falls through the horizon or goes through the boundaries of this domain, we are dealing with an open problem, and that makes these differential operators non-Hermitian and allows them to have this imaginary or complex eigenvalues. So far, so good, but there are lots of properties of non-Hermitian operators which are, while the eigenvalue problem per se looks very similar to what we usually do for Hermitian operators, the details are usually much more complicated. And for everybody who has already calculated quasi-normal modes, and probably all of you have done it, you will have noticed that it's much more complicated for numerical schemes to approximate quasi-normal modes, even in ADS, than it is to, say, get numerical solutions for Hermitian problems. So I remember when I did one of the first quasi-normal mode calculations for this brain embeddings, I tested my algorithm on the harmonic oscillator and the discretization, like with 100 points, I got like 25, 40, 50 eigenvalues of the harmonic oscillator without any problem. And so I said, okay, that converges very nicely. And then you go to put and try to apply this algorithm to quasi-normal modes. And you notice you get like the lowest one on a grid of like 100, and then you have to go to grids like 1,000 or so, and then you get probably 10 quasi-normal modes, things like that. So it is much more difficult to calculate, even by numerical approximation schemes, to calculate these quasi-normal modes. They are not complete. Usually from quantum mechanics, we are used that eigenvalues of Hermitian operators to span a complete basis in our vector space. Now, this is not true for QNMs, for quasi-normal modes. Not all initial conditions can be expanded into quasi-normal modes. It's only an asymptotic expansion, which is valid at sufficiently late times. Another property is if you choose just these coordinates, which I have shown in the beginning, this usual Schwarzschild coordinates, and it turns out that the wave function that you calculate, it's actually singular on the horizon, because the imaginary part, so it wants to be damped in time, so gamma, that has to be negative, but then you go with r star to minus infinity, and this blows up exponentially. So actually the wave function isn't really well defined in these coordinates. And so they don't have any Hilbert space. They are not members of any Hilbert space or anything like this. And so it turns out that in some sense you can repair some of these shortcomings, but possibly not all. So it seems that what you repair in one place, you get back on another with some bad behavior. So what are pseudospectra? Pseudospectra try to answer the question, how robust are the eigenvalues under small perturbations? So we know in quantum mechanics, for example, when we have some Hamiltonian, which we can solve exactly, then there might be a Hamiltonian which is in some sense close to this original Hamiltonian, and we cannot solve it, but we can hope to change to calculate its eigenvalues and eigenfunctions in a perturbation expansion. And then when the operator is sufficiently close to the perturbed operator is sufficiently close to the original operator, then there's actually a theorem which guarantees us that the eigenvalues will also change very little. Now, there's no such theorem for the non-Hermitian operators, and so you have to ask how much can an eigenvalue move in the complex plane if you modify your differential operator in some manner, in some small manner. And I will come to how to measure what is small. So this is the essential ingredient of this theory of pseudospectra. So what you do is you define what is called a resolvent, which is this operator. L is your differential operator, and Z is just some complex number. And then the spectra are the locations in Z where this operator isn't defined, or morally speaking, where this goes to infinity, which includes, of course, the eigenvalues. So morally speaking, yeah, spectrum is the points in the complex set plane where this resolvent goes to infinity. That's certainly true for the eigenvalues. And you need something in order to measure the size of a perturbation. And what you do is you introduce something which is called the operator norm. So you define the space of functions on which your operator acts, and then you look what is sort of the maximal action your operator can have on that space of function, which is encoded here as the supremum over all functions of your function space, L acting on this function is divided by the norm of this state or this function. So the definition of the pseudospectra is based on that, and there are three equivalent definitions. The most important one, which we used, is this one. The pseudospectrum is simply the points in the complex plane where the resolvent is bigger than, where the norm of the resolvent is bigger than some 1 over epsilon, where epsilon is some small number. Of course, if the resolvent is infinite, then you directly recover the spectrum, but the pseudospectrum is just saying where is the location, the region in the complex set plane where the resolvent is very large. And so you can reformulate this in the second way. You can ask, is there a perturbation to your original operator which is smaller than a given epsilon? And then you define the pseudospectrum as all the points that can be that lie in the spectrum of a perturbed operator where the perturbation is at most of order epsilon. And then there's a third one definition which asks if there is almost an eigenvector, which is within epsilon being an eigenvector. But it turns out that mathematically the three definitions are the same. And for us, probably the most interesting ones are the first one, which gives you a calculational tool of how to compute pseudospectra, and the interpretation saying that once you have the pseudospectrum, you know that there is a perturbation of your original differential operator of a given size, which moves the eigenvalue to a new location within this pseudospectrum. Okay. And so here's the, okay, here's another thing called the condition number, which is this ratio of the norm of an eigenvector U, the norm of the eigenvector of the adjoint operator divided by its inner product. Now for a Hermitian operator, that condition number is always 1. And it turns out that if you had a perturbation, a small perturbation to your original operator, then you can show that the eigenvalue can move at most in a small epsilon expansion, has to move within a region which is smaller than epsilon times the condition number, right? So this gives you a criterion by which you can call an eigenvalue to be stable under perturbations or unstable. So if you add a perturbation and the eigenvalue moves by something which is actually smaller than the size of the perturbation, then you would call this stable. Against this perturbation, the eigenvalue is stable against this perturbation. But if it moves a distance in the complex plane which is larger than the actual size of the operator as measured in your operator norm, then you would call this to be an unstable point in the spectrum. Okay. And of course, so for us, you can basically say that you can call something to be small in the complex plane where the eigenvalues live. If say if the perturbation is small, if epsilon is much smaller than the typical distance between the eigenvalues. And of course, in the simplest case for ADS, the typical distance by the eigenvalue, between the eigenvalues is always given by the temperature, since it's the only scale in the game. Okay, so I told you already that in these usual coordinates, the Schwarzschild coordinates, where I have this outgoing wave boundary condition, the wave function is actually ill-defined. And so what can you do? Well, you can choose better coordinates. And so far in the literature, there are 2 coordinates that have been used for these purposes. So one are infalling Eddington-Finkelstein coordinates, which are very standard, and many people have used this already for calculating quasi-normal modes in ADS. And there are also these choice of coordinates, which are called regular coordinates. And in the Penrose diagram, so here's the Poincare patch of an ADS, planar ADS black hole. It's these blue lines here, which are these regular coordinates. So what they do is, at the boundary, they look just like the Schwarzschild coordinates, but on the horizon, they look like the infalling boundary, the infalling Eddington-Finkelstein coordinates. So this choice of coordinates has certain advantages, and as it turns out, also certain disadvantages. So I will comment on this in the coming slides. So now we need something. I told you some of the things. Many of the things I told you. The essential ingredient is that we have to measure. We have to get a notion of size. We have to measure if something is large or small. And so mathematically speaking, what this means is that you have to introduce a norm. And you have to choose, you give a physically motivated norm. So of course we want to measure something which is physically meaningful. Something should be small if it's also small in a physical context. So the general suggestion, so to speak, if you have a physical problem and you want to know if it's large or small, want to have a good notion of the size of a perturbation of a differential operator. So the appropriate norm is the energy norm. So what we do is we take our favorite field, which for the moment will be just a scalar field, say, we calculate its energy momentum tensor, and we compute its energy on a fixed time slice in these different coordinate systems. So here, for example, in Schwarzschild coordinates, that's the energy for a scalar field. And now you can show that the energy is actually conserved here, which is a bit of a conundrum, because with these infalling boundary conditions, we know that the amplitude is exponentially decaying. So that's pretty weird. But of course, the point is that the amplitude also goes to infinity. So that's probably the reason why the amplitude has to go to infinity, because the energy wants to be conserved. So that's of course a quite singular situation. In these infalling boundary conditions, it's much better. You can calculate the energy, and you can see that it actually decays. So dVE over dV is strictly negative and is proportional to the time derivative in the slide-like time on the horizon of the scalar field. And then here, this is the energy in these regular slices, coordinate slices. And here you have a similar equation. Again, the energy, the time derivative of the energy is given by the square of the time derivative of the field at the horizon. So this really shows you that the energy decays, and it decays, and it's proportional to the time derivative of the field on the horizon. So this is what you want. And so now you can, what we did then, we chose this these regular coordinates and reformulated this complicated second order differential equation as a proper eigenvalue equation. So in the usual, if you just write down a wave equation, this wave equation will be second order. It's also second order in time, which means that you don't generate a proper eigenvalue problem because the frequency will always appear squared. Yeah, and as a side remark, if you choose Eddington-Finkelstein coordinates, then you also don't get a proper eigenvalue problem. What you get is a so-called generalized eigenvalue problem, and makes the interpretation probably a bit more complicated or different. But in principle, it's possible, and it has been done by the group around Christiane Pantelidou. They have studied this pseudospectrum in infalling Eddington-Finkelstein coordinates. But I'm not sure if you can reformulate it. So the drawback is that you cannot reformulate it as this nice standard eigenvalue problem. Now in these regular coordinates, you can do that. You can rewrite the differential operator in this matrix form by introducing a new field variable, which is just the time derivative of your scalar field. L1 and L2 are some differential operators, which look like that. And this rho is just a radial coordinate, F the blackening factor, never mind. And then the wave equation just boils down to an eigenvalue equation like that. And it really looks precisely like a Schrödinger equation where L replaces the Hamiltonian and omega is ID over dt. So it looks really like a Schrödinger equation. But if you choose the energy norm based on this expression for the energy, you can calculate what is the adjoint by just doing partial integrations, and it turns out the adjoint is almost the same operator, except for a term that acts only on this lower corner, which is here the time derivative of the field written as a field by itself, and with a delta function on the horizon, which is what you expect because all the dissipation and all the non-hermiticity comes from the horizon. And so if you just do the usual thing as you would do, say, calculate the time evolution of the inner product of a state vector in quantum mechanics. If they apply this now to the time evolution in terms of the state vectors here in this energy expression, then you find that of course, the time derivative is given by this operator and its adjoint operator, and they almost cancel except for this term, which gives you a contribution on the horizon. So again, you recover from this operator formalism here, this matrix formalism, that the energy decays and the decay rate is given by the amplitude of the time derivative on the horizon. So that's a very nice property of this coordinates. And then the question is, how do you do this in practice? Well, in practice, you employ some numerical approximation scheme. And what we do is what is sort of state of the art nowadays. You employ so-called pseudospectral methods. They are also called pseudospectral, but they have nothing to do with the pseudospectra. So one has to be careful here. Pseudospectral methods means that you approximate your functions by linear combinations of Chebyshev polynomials on a given interval, and the pseudospectra are something completely different. So then you can translate all these differential operators into some matrix operator, and you can calculate the operator norms as the infimum of the singular value decomposition of this matrix that you get. So this is basically, you have a matrix A and A adjoint, you multiply the two, and then you look to the lowest eigenvalue. And so then you can look for the values where this operator norm is smaller than a given epsilon, or the inverse of the operator is larger than 1 over epsilon, and that you can plot in the complex plane, and that gives you some contour plots which tell you that the resolvent there is larger than a given 1 over epsilon. So here's a very simple example of how this works. That's just a 2x2 matrix with these entries. Now, obviously, this is not Hermitian in the usual sense, but it turns out to have real eigenvalues, -1 and -2. So you can do two things now. One is you choose the usual norm. You just compute the length of a vector, of this two-dimensional complex vector, in the usual norm. So you take the complex conjugate vector, multiply it, take the inner product with the original vector, and take the square root. Then you can compute these condition numbers of these two eigenvalues, and you see they're very large. They're like 50. But there's a different way. So since the eigenvalues are real, you can suspect there's probably a different way of treating this matrix such that it becomes a Hermitian or a self-adjoint matrix. And in fact, you can do that by introducing a non-trivial metric on this two-dimensional complex vector space, which I have to note by G. And in particular, the metric which does the trick is written here. And then the adjoint with respect to this non-Hermitian inner product is given like that. And with taking this metric, the inverse of the metric, multiplying, taking the transverse and the complex conjugate. And it turns out that with this metric, the matrix is actually self-adjoint. And so that explains why the eigenvalues are real, because there's a basis in Hilbert space, or a metric on Hilbert space, which makes this matrix self-adjoint. And then, of course, the condition numbers computed with this notion of inner product, they are just 1, as they should be for a self-adjoint operator. So here I've plotted now the pseudospectra of these two versions, right? And that depends strongly on what I choose as a norm. So I can choose the usual norm, and then it's a non-Hermitian operator, so to speak. And I can choose this new norm, this non-trivial metric, and then it is actually a Hermitian operator. And so the pseudospectrum looks very different. Here, for example, there's a red line, which tells you, I think it's epsilon 0.1, and there's a yellow curve, which is you can't see because it's completely covered by these red dots. And so that is precisely what I told you before. If the condition number is 1, the pseudospectrum has to be within epsilon. So what this means is, if I add a perturbation to this matrix, whose size, as measured in this particular new norm with this non-trivial metric, is, say, 0.1, then the original eigenvalues, say the eigenvalues here -2, can move at most to a location within this disk, this small disk. So then, viewed from this notion of size, this is a stable perturbation. That's a stable eigenvalue. On the other hand, if I do this and measure the size of a perturbation with this notion here, then the perturbation looks very small to me, right? It can be 0.1, which is very, very small, but the eigenvalue can move now to a much larger circle. It can move out. So the yellow ring here is now out here. And what you see here typically is that there are overlaps, very fast developing overlaps of the pseudospectra. So that's a typically spectrally unstable situation, which appears for non-Hermitian operators. Okay, so here's another example now. This is the harmonic oscillator. So here, this is usual harmonic oscillator. This is the pseudospectrum of the harmonic oscillator. You see the usual here, of course, the line on the real line. And then the pseudospectra are concentric circles around this. And of course, when epsilon, if the perturbation is large enough and the radius is large enough, then they will overlap. But you see it has this typical concentric circle structure, which indicates that the spectrum is stable. So the eigenvalues of spectra is stable. And that means that you can do perturbation theory around the solutions of the harmonic oscillator and should get good results. On the other hand, if I make the operator by brute force non-Hermitian by taking the eigenfrequency or this constant C to be a complex number, then the pseudospectra look like this. And so what is it here? This is again the log of the operator norm. And so here, for example, this is 10 to the -2. So that means a perturbation which is of size 10 to the -2. It can move this eigenvalue very, very far out into this plane and very far away from the original operator, from the original eigenvalue. Okay. And that's the typical behavior for this non-Hermitian problems. Okay. So after all of these toy models, let's do this now for the quasi-normal modes of ADS. And here I've plotted, we have two plots. The one is at zero momentum, so that's a massless scalar field at zero momentum and a massless scalar field at some large momentum. And here I've done several things. First, the color code is the logarithm of the operator norm in this complex plane. So color, for example, green means that quasi-normal modes appear there if you add a perturbation of the size 10 to the -5 as measured in this now energy norm to your original Schwarzschild original differential equation, which you derive from the Schwarzschild black hole. And the perturbation of order 10 to the -5 can move an eigenvalue out here, right? So, and what you see is this color coding, the further you go down in the complex plane, the more unstable the modes become, so they can move far away along these contour lines for smaller and smaller perturbations. And this is also sensitive to the momentum. So if you take, for example, momentum, a large momentum, then you see here, for example, the lowest quasi-normal mode looks much more stable than before, but it's also an effect because it's much closer to the real axis. So it turns out the closer the quasi-normal modes are to the real axis, the more stable they become. And here, what I've done is we have chosen some. Now we have translated everything to some finite matrix at some discretization prescription, and then we can add some random matrices which represent changes in the potential of the scalar field in ADS. So we do random perturbations of the ADS of the potential of the scalar field of a given size, 10 to the minus 1 to 10 to the minus 7. And you see, for example, under a perturbation of 10 to the minus 3, well, we can say, yeah, probably the second mode here becomes unstable, but the first mode looks pretty stable against such a situation, because these random perturbations, they are denoted here by this light blue dots, whereas the dark blue dots are perturbations of order 10 to the minus 1. So perturbations that act like potentials or random potentials for scalar fields in ADS, they give you, they are captured by these dots here. Whereas the contour lines, they consider all possible perturbations in this matrix I have. And again, and what you see is that actually it turns out that under small perturbations, these quasi-normal modes turn out to be quite unstable. And so, yeah, so here there's some detailed zoom in into the lowest quasi-normal mode. We look to the stability criterion, where we say that the perturbation, we call this spectrally stable if under a given perturbation, the eigenmodes moves less than epsilon, corresponding to a condition number of 1. And it turns out that under such local random variations of the scalar field potential, for large enough momentum, that is indeed stable. So you see that this is the circle here of, I think it's epsilon 10 to the minus 1. Yeah, 10 to the minus 1. And you see all these points lie inside. So it looks quite stable, but for large momentum, but for small momentum, it isn't, because there are points outside that circle. So it's even the lowest mode seems to be unstable, and it's even unstable under local random perturbations of the potential. And then you have also tested some specific forms of potentials. So there are 4 different forms of potentials, some which are concentrated near the boundary. It turns out they have very little effect, and modes which are more concentrated on the horizon change the, say, if you want the effective mass of the field at the horizon. Of course, at infinity, we keep the field to be massless, right? So we don't want to change asymptotic boundary conditions, but on the horizon, we can introduce perturbations. So one way thinking, for example, if you have a complex scalar field and it's coupled to a gauge field and a switch on a chemical potential, then the effective mass, of course, changes in the infrared and near the horizon. So this is sort of mimicked by this choice of potentials. And you see that the potential which has the strongest effect on the quasi-normal mode spectrum is the one which is large at the horizon and which has many wiggles. That's the upshot of this. So sort of short wavelength perturbations which are there on the horizon. They disturb the quasi-normal mode spectrum the most. Okay. We were not the first ones who did this in the context of the ADS, in the context of quasi-normal modes, to calculate the pseudospectra. To my knowledge, the first people who calculated this in a systematic manner was Jose Luis Jaramillo and his collaborators in this very, very beautiful paper from 2021. And of course, they were interested in asymptotically flat space-time, Schwarzschild black holes. Here's the pseudospectrum plot from their paper. The upshot is basically similar. So this quasi-normal modes turn out in this formalism to be quite unstable. There's also a recent review from August by this UK. Okay. So of course, when you have this instability now of this quasi-normal modes, many of the ideas we had about quasi-normal modes are sort of now, there's some question mark, right? Can you, given that also in asymptotically flat space, these quasi-normal modes under very small perturbations can move very far, and there are certainly random potentials, right? If a black hole merges somewhere far away in the universe, and then you capture the gravitational waves. It certainly has moved through the gravitational potential of, say, galaxies and stars and whatever until it arrives to you. And there's some random perturbations on the potential, and they have they at least potentially can change the location of this Quasinormal quite substantially, at least according to the pseudospectrum analysis. So it might be very difficult to realize this program of black hole spectroscopy. And for us in holography, I think it also means that we have to rethink a little bit some of the things we say about say, convergence of hydrodynamics, because that depends on the location really where quasi-normal modes collide somewhere in the complex plane. Here, so far, we have only investigated really the usual quasi-normal modes, which have real momentum and complex energy. Of course, you can choose other slices with complex momenta and real frequency or somewhere in between. And these locations where the modes collide are typically somewhere in complex frequency and complex momentum. And also there, of course, now the question arises, how stable are such collision points under perturbations? So all of this, I think, needs to be investigated further. However, there are a couple of mathematical problems which so far I have swept under the rug. So now it's time to discuss some shortcomings of this. So one of the shortcomings is that there's a general problem with this energy norm. On the horizon, we have this ingoing and outgoing modes, and it's easy to impose, say, in this Chebyshev approximation, it's easy to sort of impose these infalling boundary conditions, because it turns out that you don't need to introduce any boundary condition, because the modes that interest you are regular on the horizon, and polynomials are automatically regular on the horizon. So at any finite number of polynomials, you can reproduce only these regular boundary conditions, but not in the large n limit. In the large n limit, since polynomials are dense in the space of functions on an interval, they can even converge to slow, but they converge to non-regular solutions. And that means as you crank up n, the number of points in your discretization scheme, you are able to approximate better and better also the outgoing solutions. And it turns out that for the energy norm, these outgoing solutions, or the guys which come out from the horizon, they also have finite energy. So they contribute to your energy norm. And what happens then is that from a certain imaginary value on, every point in the complex plane, strictly speaking, belongs to your spectrum, is a point where the resolvent is not defined, or the operator norm of the resolvent isn't defined. And so there is, strictly speaking, not a discrete point spectrum from this perspective. Now, in mathematics, how people deal with it is they introduce what is called Sobolev norms, which, morally speaking, are higher derivative terms, which you add to your notion of norm. And then that can bring the line where this happens, where the outgoing modes or these non-regular solutions can contribute, brings it down further and further, one step for each derivative term you add. So you at one derivative higher, it goes one step down, and then for two derivatives, you get another step down. But of course, in physics, we cannot just arbitrarily add higher derivative terms. We know that, we think strongly that GR, and especially in the ADS-CFT correspondence, when we treat two derivative gravity, we're talking about an effective field theory. And if we want to improve on that, we have to add higher derivative terms in a specific number, and then probably we have to add specific higher derivative terms. And in any case, the two derivative action is valued only down to a certain length scale, right? It turns out that in the coordinates, which we like so much because we have this nice real eigenvalue problem, where formally it looks like really like a Schrödinger equation, the problem we are solving. That is even worse, because the inverse resolvent doesn't have a property in terms of operators, which is called compactness, which has the effect that in the large n limit it doesn't really converge. So that has been pointed out. Well, I guess it's in this paper by Warnick, which is the mathematician who understands that all of this much better. In physics of some first steps to understand this better has been done recently in this paper by Boyanov, Cardoso, Destunis, Jaramillo, and Macero. And so it's a little bit of a dilemma. What do you do there? Because strictly speaking, this large n limit doesn't exist. Now you can say, of course, as a physicist, are we really interested in going to large n because we are dealing with an effective field theory? And so what I also showed you is that the most dangerous perturbations, at least for these potentials which we added, the most dangerous perturbations are the ones which have many wiggles. And of course, when you have more and more wiggles, your derivative terms become larger and larger. And at a certain point, you are certainly beyond the validity of a two-derivative action when the gradients become too large. But these are precisely the terms which you can add when you crank up the number of points in your discretization scheme. So that raises the question, if they're physically well-motivated, sort of maximum n that you would like to implement if you stay within the realm of effective two-derivative gravity. And that would mean that at this particular resolution of n, you are doing fine, and you can apply these methods which we use. But of course, the question is what is a good value of n? So, for example, a naive guess would be choose like 1 point, at most 1 point, a resolution such that you can capture at most 1 point within a distance of Planck length from the horizon, which is a ridiculously large n. So I don't know if this is any practical usefulness. And another issue that arises and for us is I've used this energy norm, which is just what you do in field theory, classical field theory, on whatever space-time. You can compute the energy momentum tensor and the energy of a field configuration. That's nice. Good. But it's classical field theory. And the question is, does this have a holographic interpretation? This is less clear. So I don't know if there is any holographic counterpart of what we call the energy norm. It also has to be said that this pseudospectra, they depend very much on the slicing. So they have different properties in this infalling Eddington-Finkelstein coordinates than in the slicing we chose. If we calculate just naively quasi-normal modes, the way we always do it, it turns out that actually these regular coordinates are very good. You capture typically on a grid of n points, you capture like n over 2 quasi-normal modes, which is much better than what you can do typically in infalling Eddington-Finkelstein coordinates. But then there are other drawbacks. So there are still lots of questions. So I probably just, it's 5 o'clock, probably I stop here. I've discussed already the issues that exist, mathematical issues, which at least we need to understand much better. But the upshot is that I think what stays of this is that this quasi-normal mode, the locations of the quasi-normal mode and the quasi-normal mode frequencies are something very subtle. And also ideas of trying to identify some holographic piece of material or some, say, which has been propagated, the idea of trying to implement, say, ADS, black hole physics on a quantum computer, and then as a signal looking to the quasi-normal mode frequencies might be difficult because small perturbations might change the quasi-normal mode frequency in very substantial, in a large way. That is, I think, the lesson so far from this investigation, which is stable. Okay, that's all I have to say. Thank you.
Okay, thank you very much, Karl, for the interesting talk on this exciting topic. Thanks a lot. Do you have time for questions and comments from the audience? Any question? Okay, let me start myself. I think, as you said, okay, these things have been all done in the bulk, in the ADS side. I think maybe in 3 dimensions, ADS3, we have more control on our calculations, and in particular, on the dual field theory and CFT, that would be a good place to check these things in a more controllable way. Then my question is, what could be the my understanding is that this kind of perturbations in the bulk are kind of bottom-up engineering perturbations. So what could be the dual of these perturbations for example, 2-dimensional CFT living on the boundary?
Yeah, that's a good question. Well, one of the things, what we probed was, we had these local potentials, and they had large effects when they were not zero on the horizon. And so, for example, you could study a scalar field which might live in a random chemical potential background. Then probably that would be similar to some of the aspects we studied here. Because it would couple, you would look just to the wave equation for the scalar field and take the gauge field background as a background belonging to the background, but as a random field. It can be large, small, and then it might have a large effect on the
even we may make the temperature a random field on the boundary, like the chemical. Okay, great.
So that's more difficult because temperature, making temperature a random field, because temperature is is actually only defined in equilibrium. So but you could try to model this again as sort of every in a one-dimensional wave equation you have some effective potential which comes from the gravity part and you could interpret this also as perturbations of in this. So and that would keeping the of course the coordinate value of the horizon fixed, but then letting it actually fluctuate, which would mean, of course, the horizon coordinate value is just still 1, but outside the space-time looks slightly different.
I see.
So, yeah.
Yeah, thanks. Okay, we have a question from Ove. Go ahead, please.
Yeah, okay. Hello, very nice talk. I have several little questions. The first question is, did you know about similar work on pseudospectral techniques for BTZ black holes? Is there something more explicitly? Because in this case, one could actually use also the underlying group structure, Lie algebra representation theory, and so to relate it to this pseudo spectral techniques. And maybe this could help to better understand the origin of these various directions. There's this very strong divergences in other directions let's call it in function space, where it's more or less not so sensitive.
Yeah. No. I don't think so. So most of the work which has been done on this pseudospectra of Quasinormal modes is done by people coming from the gravity community. They are mostly interested in asymptotically flat spacetimes. There is some recent work on asymptotically anti-de Sitter spacetimes, but I don't think they look to PTZ. This is certainly a situation where one would have more control. I guess it's worth investigating that further. Yeah.
Yes, that's one point. The other point is maybe you observed it in your calculations, numerics, and so on. Also, that this pseudo spectral techniques, they are actually in a certain way, they are very non-sensitive to the direction of the perturbation in the function space. When you usually the pseudospectrum is defined by this kappa term, this which is given actually the scale for with which the perturbation is mapped to the operator itself. And when you are choosing, yes, exactly here, yes. But what one could try is to not to consider the whole function space, but to decompose this function space in several sectors. And you will find that you will have, when you are considering kind of functions, it will be very sensitive, or this kappa will be very high, and in other directions will be very low. So this means that in this,
definitely,
you may call it a generalized rigged Hilbert space or something like this. There you will have directions where this perturbation theory will work very well, and other direction where a very small perturbation is sufficient and it will blow up completely. So, and it's very similar in group theory. There you have, when you have perturbations, or when you're using representation theory, when you're going over compact homogeneous spaces over compact components, everything is fine. It's close to usual self-adjoint operator perturbation theory. And when you're going to non-compact ones, you are getting something perturbations along the event horizon in this representation. And these, when you're doing something there, it's blowing up immediately. And you are needing Harish-Chandra techniques and all these things. And the guess would be that these things are extremely closely related. It would be nice to see these structures, how they are looking explicitly. Are you aware of something like this already in the literature, or is it not yet done?
No, unfortunately, I'm not aware of that, but I cannot, say that it has not been done. I don't think so. It sounds precisely, what we observe, because indeed, the dangerous perturbations which really make the thing blow up and not converge are the ones which are very close to the horizon, have many, many wiggles, and so.
It's exactly what you are using in different coordinate systems that you are approaching the horizon. So you have a general physics and you have different coordinate systems, and this is something similar what is in group theory and representation theory, that you have compact, you are going along compact slices or non-compact slices, and these things are behaving absolutely different. And when you turn it to parabolic slices, it's becoming even blowing up immediately, and you are getting something like involved like twistor approach and all these things. So it's exciting topic. I'm just wondering whether you are already connecting this to this pseudospectral techniques.
No, I'm not. Actually, I'm not aware of this. So I would be very happy to learn more if you can tell me more about this, or send me some references, and I would be happy to learn more about that.
Yeah, okay. We might discuss it afterwards a little bit.
Okay.
Okay. Thank you very much.
Thank you.
Okay, thank you. Any other question or comment?
Hello.
Hi.
It was a nice talk. Could you make some comment on some connection between the pseudospectrum and some pole skipping points where the Green's function is not very well defined thing?
Yeah. So let me see. So the pole skipping points are they are directly defined locally on the horizon, right? As far as I remember. Also, they lie at these special points, which moderately speaking are like the Matsubara frequencies, right? So it's omega is basically minus IN or something like this.
Right. Matsubara frequencies.
Yeah. So it turns out, there are special points in the spectrum. Usually, from our perspective in holography, we would not call these quasi-normal modes, because actually, since the residue of the holographic Green's function vanishes there, It's not what we would call a quasi-normal modes in holography. So in this mathematics paper, they say there are still genuine quasi-normal modes. Question: are they stable? My guess is they're stable because there's some sort of it's really just locally determined, locally on the horizon. So I would guess they are pretty stable. But
yeah, I was just thinking of some.
Yeah.
I was just questioning about the connection between these. Are they connected somehow?
Yeah. So
This.
how is this? You can characterize these pole skipping points as the points where you can actually not really distinguish between in and outgoing, right?
Yeah. Right.
Yeah.
Right. Okay. Thank you. Maybe I need to check this.
So, but concerning, so for example, if you calculate in these numerical methods with Chebyshev discretization, you actually don't find those points. As far as I remember, they are not there.
Whether means I was asking whether in that spectrum that you were showing where this quasi-normal modes, suppose for this ADS5, you were showing some spectrum, this quasi-normal modes and this pseudo-spectrum also.
Here in the
Not here, there's some colorful spectrum you're showing.
Here.
Yeah, right here. So
Yeah.
here, can you tell me the location of the pole skipping points? The pole skipping
I
points.
think they would always
the
be
omega.
here. Yeah, they would
Oh,
always.
sorry,
be
this is their omegas. Yeah, omega
Yeah,
will
they
lie
would be
here also, like the frequency.
Yeah, exactly. So zero real part and the imaginary part. I think in this normalization it would be probably at -2, -4, and so on.
Okay.
Yeah.
Thank you.
Okay.
And yeah, and when you say about the connection between this you said somewhere the hydrodynamics and quasi-normal modes. In the beginning, you were saying about the hydrodynamics and quasi-normals. Generally, the hydrodynamics is defined when this omega k is like very small, tends to zero limit.
Exactly.
But
Yeah.
here, these omegas are not like not very small, like when you talk about this quasi-normal modes.
Yes.
So,
it
like,
depends
how
on
can we say that thing?
Okay, good. So I guess the idea is how far can you go and try to describe theory by just one mode, the lowest mode, say.
Okay.
Right.
Okay.
And
still, that's not like we can you say the lowest mode is also like tends to zero?
The lowest mode, yeah, because of this conservation law, you would expect that it tends to zero at zero wavelength.
Okay.
Right. Now here there is something in connection to the pole skipping points because the diffusive mode, since it's imaginary, right? It has to hit for a specific k value, right? Somewhere along here.
Yeah,
it has to hit the pole skipping point. And it's somewhere around here where actually this
the collision of the this first hydro and non-hydro, there lies the pole skipping point, I guess. That you were saying the collision of this hydrodynamic mode.
I think the collision is somewhere. Okay, so I'm not completely up to date with this, but the collision point I think is some general complex values of omega and k.
Yeah.
Yeah.
Sorry.
There's the collision point is at some general complex values for omega. Yeah.
Okay. Okay. Thank you. Yeah.
Okay, very good. Thank you very much, Karl, again for this nice talk. I think we can stop recording at this point and then time to have some more informal questions.